Okay, in this video we will explain the notion of equivalent systems and solutions or a solution of a system. Let me remind you that the notion of equivalent is not new for us. For example, if we have 2 over 4, we say that this is equivalent to 1/2, and this is equivalent to, let's say, like 32 over 64, and we have some rules that we can, of things that we can do to that fraction to make it equivalent, right? If we multiply by the same number on the numerator and the denominator, then we get something equivalent. We are going to say that a system, two systems are equivalent if their solutions are the same, but we're going to be more clear about that. First of all, then, since we're going to explain equivalence of systems based on the solution, let me just say that if we have a linear system like this, if we have a solution, a natural way to write a solution is like x1 equal x1, x2 equal x2, and xn equals to sn. But instead of saying that this is a solution, we're going to say that s1, s2 up to sn is a solution. Notice that somehow we're using the order of the vectors to say that the first entry goes with x1, the second entry goes with x2, and so on. Let me do an example. If we have x1 plus x2 equal 2, x1 minus x2 equals 0, then we notice that, let's say, 1 and 1 is a solution. And notice that this means that x1 equal 1 and x2 equal 1 is a solution. Let me do another example. If we have x1 plus x2 plus x3 equal 4 and x2 plus x3 equal, let's say, 2, then we have that x1 equal 2, x3 equal 1, and x2 equal 1 is a solution. But instead of writing it like this, we will write it like 2, 1, 1 is a solution. And we can also check that, for example, 2, 0, 2 is also a solution. This means that x1 equals 2, x2 equals 0, and x3 equals 2. We can check that. Then the whole point here is that instead of giving the solution like this, we are giving the solution as a vector. We are also going to consider the solution set. And the solution set is the collection of all solutions. Notice that here we have an issue that we need to deal with, because sometimes a system may have infinitely many solutions. Then we need to learn how to describe a solution when we have infinitely many solutions. So maybe I should do an example of a solution with infinitely many solutions. Let's say that we have x1 plus x2 equal 2 and 2x1 plus 2x2 equal 4. We notice that essentially these two are the same equation. Then we only need to worry about solving this one. And then we can say that here x2 can be anything, and then I will write just x2, and x1 is supposed to be 2 minus x2. Then we're going to describe the solution set as the set of points of this form such that x2 is a real number. Remember, this means belongs to or is an element of, and these are the real numbers. Then here we have infinitely many. If we pick, for example, if we make x2 equal 5, then we will have here -3 and 5 is a solution. Then anytime we want to see a solution, we just pick a real number and we get a solution of the system. Please do this homework. There are some systems that they look kind of weird, but they show up so many times that I think it's a good idea to point them out. Notice that according to this definition, I'm allowed to have this system like 0x1 plus 0x2 equal 0. This is a possibility for a system. We can say this is a system with two equations and two variables. Notice that this is equivalent to say that x1 plus x2 equal 2 and 0 equal 0. Then this is something that may show up, right, as a system. Here I'm just saying that A21 is 0, A22 is 0, and B2 is 0. Then as a definition, it looks weird, but it will show up a lot. Another possibility that we may have as a system is something like this, right? We can make A21 equal 0, A22 equal 0, and B2 equal 3. Then in this case, this system will look like x1 plus x2 equal 2 and 0 equal 3. Then we may have things that looks like that. It is strange, but that will show up a lot, those systems like this. Then now we have the notion of what is a solution of a system. And now we can define what are equivalent systems. We say that two systems are equivalent if the solution set is the same. And let me write that down. Let's say that two systems are equivalent if their solution sets are the same. Let's see some examples. Actually, we are very familiar with this type of example. If we have the equation 2x plus 3 equal 4, right? This can be viewed as a system of one equation with one variable. Notice that we are familiar with things that we can do to an equation so that we get an equivalent equation in the sense that we get the same system. We can subtract the same number in both parts. And then technically what we are doing is we are replacing this system by this system. We can multiply by a number that is different from 0. And then if we multiply by 1/2, we get that this system and these systems are equivalent. And that means that they have the same solution. We're already familiar with some things like that. But when we have a system of equations, let me just do a 2x2 system. Let me do the easy one that I have been dealing with. x1 plus x2 equal 2. And x1 minus x2 equal 0. Geometrically, the line x1 plus x2 equal 2 is this line. This is 2 and this is 2. And this is the line x1 equal x2. This is the x1 axis, x2 axis. Then here we know that the only solution is the point 1, 1. Some basic things that we can do. We can swap the two equations, and it is very clear that we get the same system, right? Then, in general, we can do that. If we have here m equations and we select 2 and we change the order in which they show up, we get a system that is equivalent. We can do that. What else can we do? We can, if we multiply one of the equations, let's say that I start with this one and I multiply by 2. Then it is very clear that in this case we are not changing the solution, right? Then in general we can do that. We can take an equation and multiply it by a number that is different from 0. We cannot multiply by 0 the whole equation because that will change the system. The other thing that I can do, let me do it here. The third thing that we can do to the system is we can pick one of the equations, and then we're going to leave that equation. We're going to keep that equation, but we can multiply that equation by any number. Any number, it could be 0, it could be any number, let's say 2, and I can replace the other equation by that equation plus that product of the first equation with that number 2. Then here, what will I get? I will get 3x1, right, minus, it will be plus x2 equal 4. This is something that we can do. We can change the equation. We keep one of the equations, we keep it the same, and the other equation that we have selected, we just keep it, but we add a multiple of the other. Essentially, we're changing one of the equation by the same equation plus a multiple of the other. I'm curious about how these two lines looks like. The first line is x1 plus x2 equals 2. Here is 2, and here is 2. And then we have these lines. And now, how do we graph this? What happened when x1 is 0? When x1 is 0, x2 is 4. And when x2 is 0, x1 is 4/3. 1/3, 2/3, 3/3, 4/3. Then the other line would be like this. And something that we can check is that the two systems, they have the same equation. 1 is still the solution. But these are the three types of operations that we can do to the system to change it into an equivalent system. Then let me just write them down. We can swap two equations. We can do this in general. This is the first thing that we can do. We can swap two equations. We can multiply one equation by a non-zero number, and the other thing is we can change one equation by the equation itself plus a multiple of another equation. These three things can be done to solve any 2x2 system. And let me just solve a 2x2 system using these three things, and then we stop here. Let's suppose that we have 2x1 plus x3 equal 4, and x1 minus, sorry, here is x2 minus x2 equal 7. Then something that I can do, I can just keep the same equation on top, 2x1 plus x2 equal 4, and I can change this by the same equation plus a multiple, but this time I'm going to keep just 1, then it will be just the sum of the two. Then I will get 3x1 plus 0x2 equal 11. Once we have one of the variables is gone, I can solve for x1. x1 is 11 over 3, and once I have this, I can replace that in the first equation, and I get 2 times 11 over 3 plus x2 equal 4. That means that x2 is 4 minus 22 over 3, which is 12 minus 22 over 3, which is negative 10 over 3. Then the solution of this system is 11 over 3 and negative 10 over 3. What we're going to do next, in the next video, is we're going to find out a methodical way to use these three operations to solve any system. But by now, this is a little not organized, but we're going to find a way to use these three operations to solve any system. And I think I'd like to stop here. Please do this homework.